find x and y for this. Again, I'll note for these problems, we're often not making a free body diagram. There's no equilibrium equations. It's really just the math. Now, we will look at an example that does combine the two, but in this, we'll do a diagram, but it's not a free body diagram. So I will draw my shape on the coordinate system. It's bound by the top by this y equals x. It's bound on the right, or kind of on the bottom, by this curve y equals x cubed over 9. And then at the top, it's being bound by y equals 3. And on the right, it's being bound by x equals 3. So this is the shape we're looking at. In order to find centroid, we're first going to have to find the area of this shaded shape. We want to then decide, do we want to use a vertical rectangle or a horizontal rectangle to do that? So the key here is that's going to determine which one might be easier is we look at the bounding curves, and basically what we can see is which variable is easier to isolate without producing a radical is usually our goal, because that's going to make the integral step harder. So we see that x is 3 is 1, y is 3 is 1. We don't have to worry about that. What we have to worry about are these two curves. Is it going to be easier to make x by itself or y by itself? And it could be easier for one than the other, or it could be easier for both, that we put everything in terms of y or in terms of x. So sometimes there's not necessarily a better way to do it. For the top function, we have y equals x. So either we put everything in terms of x or in terms of y. Either one is equally okay there. So that doesn't help us make a determination. But down here, we have y equals x cubed over 9. So already y is isolated, and then our right-hand side we just have a polynomial. If I wanted to isolate x, I'm going to have to take the cube root of both sides, and then I'll have x equals a cube root of y expression. And doing the integral of that is not going to be as easy as doing the integral of an x cubed. So what that tells me is, because here y or x are equally okay to isolate, here it's easier to put y in terms of x. This tells me I want everything in terms of x. So referring back a slide, if I want everything in terms of x, I'm going to prefer to use vertical rectangles to make this. Again, I could use vertical or horizontal, but generally for this particular one, it's going to be easier to use a vertical rectangle. And we'll see why that's the case in a minute. So I can draw my kind of general rectangle that fits into my shape. There's an infinite number of them. And because I'm using a vertical rectangle, that means that each rectangle has a width of dx. Their bases are infinitely thin, but there's an infinite number of them as we go left to right. If I had used a horizontal rectangle, their height would be infinitely thin, but there would be an infinite number of them from bottom to top. So what I want to do is I want to find what is the area of every one of these rectangles. Well, the area of a rectangle is its base times its height. The base we already know is dx. That's done for us. But we see as we go along, every rectangle, the top of the rectangle is at a different location, and the bottom of the rectangle is at a different location, and the height changes. It's small over here, it gets a little wider, and then it gets a little shorter as we go. So what we can say is every triangle will have an upper value, I'll call yu, and a lower value, I'll call yl. And if we can define these generically for any rectangle inside this shape, then when we integrate it, we have an expression to work with. So generically here, that means that the height of any rectangle is going to be this y upper minus the y lower. So I have a height times a width, or a height times a base, and that gives me the area of every one of these rectangles. And when I add up all those areas, I get the total area of this shape. So I need to define here where is the upper location for every one of my rectangles. So whether it's this rectangle or this rectangle, where is y upper located for any of these rectangles? So this bounding curve up here always defines the upper or the top of every one of my rectangles. So y upper is this curve. So it's just going to be x. So what I do here, because I have a dx, I'm going to express everything in terms of x. So y upper is equal to x. And if I look here at every one of my rectangles, the bottom of every rectangle is located on that bottom bounding curve, which was y equals x cubed over 9. So this y lower is defined by this for every one of my rectangles, so I can substitute this in for y lower. At this step, you want to make sure that if you have a dx here, everything is in terms of x. And this is why it was preferable to have y in terms of x rather than x in terms of y, because otherwise at this step I would have had that cube root expression in here, because I would have had dy if I were using horizontal rectangles. So it's just easier in this case to use the vertical. Now I have an x cubed rather than a cube root y term. Questions on finding the area of each of my rectangles. Right? So each rectangle's height times each rectangle's base. This describes every rectangle. So my first step is I want to find now the area of the shaded shape. So I can integrate dA. Everything's going to be in terms of x, so that is how I want to define my bounds here, is what's the x bounds going to be. For the vertical rectangles, I have to see at what value of x do they start, and at what value of x do I stop adding rectangles together. So in this case, the first rectangle is going to start when x is equal to 0, so that's my lower bound. And then I keep adding rectangles until I get to x is equal to 3. And then I stop, and now I've included every rectangle that's going to be inside that shape. And my dA, I've defined above here, x minus x cubed over 9 times dx. Everything here is in terms of x, so I can integrate this just like I did in Math 140. I have just polynomial expressions, so I can find its antiderivative easily. So its antiderivative of x is going to be x squared over 2 minus the antiderivative of x cubed over 9 is going to be x to the 4th over 36, 4 times 9. And I can evaluate between 0 and 3. So this is going to be 3 squared over 2 minus 3 to the 4th over 36. And then it will be minus quantity 0 minus 0, but that will just be 0 in this case because my lower bound is 0. So what I get when I simplify this is that the total area of the shaded region, I get 2.25 feet squared. I have the area. Now I'm going to be able to find the centroid of this composite shape because both the x and the y are going to rely on the value of the area because I divided by that from that previous slide. Now I need to define for any one of my rectangles what is its x tilde and its y tilde. So where is the centroid of it located with respect to my origin? And if I define it for every rectangle, then I take that weighted average, which is that integral, and then I can find the centroid of my entire shape. When I'm using a strip method, a vertical or a horizontal strip, one of these is always going to be easy to find. So if I look here at my vertical rectangles, how far is the centroid of each rectangle from the y-axis, whether I'm talking about this one or I'm talking about this one. This one has a different x tilde. What is the x tilde value for any one of my vertical rectangles going to be? If the rectangle is located at x is 1, then my x tilde value is 1. For this one, if x is equal to 2, then its distance from the y-axis is 2. So in this case, for vertically oriented rectangles, my x tilde will be at just x. And that's always true for vertical strips. For horizontal strips, it will always be true that y tilde will be equal to y. However, the opposite is not going to be always quite as easy as that. I want to know how far away is this centroid, again, for any one of these shapes. Where is its centroid located as a distance from the x-axis, or what is its y tilde value? So if I look at here, or if I look here, or if I look here, how can I determine how far its centroid is from the x-axis? The average of the upper and lower, of the top and the bottom. So it does work out the same. So this will be y upper plus y lower over 2. So it's just that average value. In this case, our y upper was x plus y lower, x cubed over 9. Oops, put that all in the numerator. And we divide that by 2. And we can split that out into x over 2 plus x cubed over 18. Now, questions on finding the x tilde or y tilde. So this is its distance, whether I'm talking about this rectangle or this one or this one. That's the generic expression I can use. And now that I'll be able to put into the integral. Now I can find, because I know the x and y location for the centroid of every individual rectangle, I can find for the whole shape where its centroid is located. This is going to be integral from, in this case, 0 to 3 of x tilde dA over A. A I already know is the 2.25. I don't need to recalculate that. It's really just the numerator that I need to figure out. Note it has the same bounds as the area expression did. It's still from x equals 0 to x equals 3. I'm going to take x tilde, and I'm going to multiply it by dA. X tilde for this is x, and dA is the same as how it was defined before. That will be x cubed minus x to the 4th over 9 times dx. So again, the product of these two terms. So that and that. If I take the antiderivative of this expression, I have x cubed over 3 minus x to the 5th over 45, evaluated from 0 to 3. Again, I'm just doing the numerator at the moment. Then I'll combine it with the denominator again. I get that the numerator is going to give me 3.6 feet cubed. The numerator is 3.6 cubic feet. The denominator is 2.25 square feet. So the 3.6 divided by the 2.25 gives me that x bar is 1.6 linear feet. So this tells me that on this shape, if I start at the origin, I go 1.6 feet to the right, somewhere along this line, if this were to scale. That's where my centroid is located. I now have to find out how far above the x-axis I have to go to find that point where I could concentrate all of its mass that would be equivalent to the whole distributed weight. Finding the y-bar is pretty similar. The only difference is instead of multiplying x tilde by dA, I multiply y tilde by dA. A remains the same. So once again, it's just this numerator that I have to work out. My y tilde is this expression, x over 2 plus x cubed over 18. And I have to multiply it by dA. So multiplying polynomial terms here, This one simplifies a little bit because this is an x and an x cubed. This has an x and an x cubed. I get x cubed over 6 minus x to the 7th over 1134. So the numerator for this expression is going to be 2.57 cubic feet. We have the numerator. The denominator is that 2.25. So the final step is we can find y bar by dividing 2.57 by 2.25, and we get about 1.14. So from the origin, we have to go to the right by 1.6. We have to go up by 1.14. So somewhere in that general area, not drawn to scale, but just graphically, that's where the centroid of this shape is going to be located.